Good morning everyone. In this lecture we see about the design of continuous slab. Myself Dr. J. Sahayaruban, Professor and Head, Department of Civil Engineering, Rohini College of Engineering and Technology, Kanyakumari. So let us see the design example. Design a one-way slab for an office floor which is continuous over T-beam at 3.5 meter intervals. Assume the live load is 4 kN per meter square. Adapt M20 grade concrete and Fe 450 high yield strength deform walls. So L is equal to 3.5 meter, Q is equal to 4 kN per meter square. Characteristic compressive strength is 20 Newton per mm square. Then yield strength 450 Newton per mm square. Let us find out the depth of the slab. So depth of the slab we have to find out by using class 23.2.6 of IS 456 2000. The span by depth ratio for the continuous slab is 26. So span by 26 is equal to 135 mm. So adapt 140 mm. So overall depth we have to provide as 165 mm. So next we have to find out the loading. First the self height of the slab we have to determine by using depth into 25. 25 is the unit weight of the RCC. The floor finish is 0.875 kN per meter square. So total working load, so 4.125 plus 0.875, that will be equal to 5 kN per meter square. Then total live load is equal to 4 kN per meter square. Live load given in the problem. Next you have to find out the bending moment calculation. Referring the chart number, that is table number 12 and 13 of IS 456 2000, the maximum negative bending moment at the support next to the end support is 1.5 GL square by 10 plus QL square by 9. So substitute the values here. 1.5 into 5 into 3.5 square divided by 10 plus 4 into 3.5 square divided by 9. So that will be equal to 13.35 kilonewton meter. Like positive bending moment at center span, we have to determine by using 1.5 into GL square by 12 plus QL square by 10. So finally we will get a value of 15 kilonewton meter. So for negative bending moment is 17.35 kilonewton meter and positive bending moment is 15 kilonewton meter. Next shear force calculation. Maximum shear force at the support V is equal to 1.5 into 0.6 into G plus Q into L. This is a formula we have to use for finding the shear force. So that will be equal to 1.5 into 0.6 into 5 plus 4 into 3.5. So is equal to 28.35 kilonewton. Next we have to check that depth of the slab. So mu limit is equal to 0.138 FCK into BD square. So substitute all the value here. Finally we will get a value of 54.1 kilonewton meter. So mu is less than mu limit. Here mu is less than mu limit, so this is the under reinforced section. Then we have to find out the reinforcement. So we know mu is equal to 0.87 Fy AST into D, 1 minus Fy AST divided by Fck into B into D. So substitute all the values here. Finally we will get a value of AST is 360 mm square. So provide 10 mm diameter bars at 150 mm center to center. So AST is equal to 524 mm square. How we can provide that spacing? That is small AST divided by capital AST into 1000. Small AST pi by 4 into D square, that is 10 square, divided by capital AST is 360 into 1000. So that reinforcement is same provided in the midspan also. So distribution steel 0.12% of B into D. So 0.12 divided by 100 into 1000 into 165. So we will get a value of 198 mm square. So provide 10 mm diameter bar at 300 mm center to center. So AST is equal to 262 mm square. So for main bar 10 mm at 150 mm center to center. For a distribution same 10 mm we are providing 300 mm center to center. Then check for deflection. The tau V value is equal to VU by BD. Substitute the value of VU and BD. You get 0.2. Then percentage of steel reinforcement 100 AST BD. So from table number 19 we have to find out the tau C value by 0.38 Newton per mm square. So tau C is greater than tau V. The slab is safe against the shear stresses. So deflection we have to check. considering end and interior spans. So L by D maximum is equal to L by D basic into modification factor. So we have to find out the percentage of steel reinforcement as 0.28. Then that modification factor we find out by 1.5. So LD max is equal to 20 plus 26 divided by 2 into 1.5. So that will be equal to 34.5. Actual is 25. That is L by D actual. 25 actual L by D actual is less than the L by D maximum value. So hence the slab is safe against the deflection control. So finally we have to draw the reinforcement detail. The main reinforcement as well as the distribution, and the spacing you have to provide. Main is 10 mm at 150 mm center to center. Distribution we have to provide is 10 mm at 300 mm center to center. This is the depth of the slab is 165. The effective length is the length of the slab is 3500. In the support we have to provide additional reinforcement support conditions. So this is all about the continuous slab and its design. Thank you so much.